Hey guys, welcome back to another episode of Captain Hook's physics problem solving. Today we're going to deal with velocity and acceleration, specifically dealing with velocity versus time graphs. Again, the problem we're going to use, you'll be able to see below this video, but I'll go ahead and put it here and we'll get started. This one should be pretty quick. There's not a lot of math today, just sort of thinking through it. All right, we have two graphs, both velocity versus time. And these graphs show the velocities of two different people running as a function of time. You will need no calculations for this, only graphs, as I said, but we'll make sure we show some kind of work, okay? All right, here's our first runner. Both start out at 0 and run for approximately 10 seconds. This guy stopped at 9 seconds, but we're doing it over 10-second interval. And our first question says, during which interval of time is the acceleration positive, is it negative for each of these graphs? Okay? Now again, we're looking at plots of velocity versus time. So the acceleration tells us how much velocity changes over that time. Just like a velocity is a slope of a position time graph, acceleration is going to be the slope of each one of these velocity time graphs. On these graphs, if you look at the slope, you can see that it's changing with time, right? So it's curved, it's not a straight line. So it starts growing, it sort of flattens off a little bit, and then it drops down. Same idea here, starts growing, getting faster, flattens off, and then starts dropping down again. Okay? So in this case, when the acceleration is positive is when we have a positive slope, when the velocity is growing. So for our first one, looks like it's growing from 0 seconds, it's growing till we get about there. So for our first one, our positive, for the first person, the one on the left, the range is from about 0 seconds to about 8 seconds, because that's when our velocity is growing, that's where our slope is positive. For our second one, this thing out of the way here, same idea. We start at 0 and we rise pretty quickly. Well, we rise here till we get about there. And again, if we follow that down, that's about 2 seconds. So our positive velocity for this one, or for the graph 2, our range is from 0 seconds to about 2 seconds. Okay? Now at this point, it flattens off and then it starts dropping back down. So as it's dropping down, our slope is negative. So from here to the end, our velocity is getting smaller. So again, on our left graph, from 8 seconds to 10 seconds. So negative is from, again, 8 seconds to 10 seconds is when we have a negative acceleration. Same idea if we look at here. When is our slope negative? For our negative, for the second one, well, after we get to 2 seconds, it flattens off right there, about there. And then the whole time, the rest of it is going down from 2 seconds all the way to 9 seconds. We have a negative acceleration. Now notice it's not 10 because we stop at 9, right? So that's sort of that one. Now, is it ever 0? Well, if you think about this logically, if we're going from something that's positive to something that's negative, it has to be 0 in between, right? So when it changes from our positive acceleration to our negative right there, so from our left graph, it's going to be 0 at exactly 8 seconds. So when we have no acceleration, or 0 acceleration. Okay? Same idea for our right graph. If we go from here, when it changes from positive to negative, right there, it's got to cross 0. So it's going to be at exactly 2 seconds for that one. Okay. All right, our last question. It wants to know which person runs further in the first 10 seconds. Now this could be a little tricky. If we think about it logically, this guy's going pretty fast, pretty quick. His highest speed is definitely bigger than this, but that could be misleading. So what we actually know is that if we were to say run, off track a little bit, if we were to run with a constant velocity, so whatever our velocity is for either person, so we're going to have time on the bottom, we have our velocity on the side. If we had a constant velocity, that means that our line, or our graph, would be a straight line. There would be no acceleration. So we go from here, and well, don't really worry about time, but straight line, okay? So if we wanted to know what the total displacement that he would have, it is actually just the area underneath the curve, the area under that graph. That gives us his total displacement, how far he's gone, because that's the same thing as saying displacement is velocity times time. displacement equals velocity times time. This is sort of just what it looks like graphically, okay? So if we do that, total area under the graph is our total displacement. Well, we can look at these graphs, and it's pretty evident, at least, that this has a bigger area. There's more under the curve. So this one has a lot more under the curve than this one does. Since there's more under the curve, the displacement's greater, so it means he's gone farther in the first 10 seconds. So in this case, it would be the runner on the right side. On the right.